Alrighty, let's go ahead and take care of the homework. So gas occupies 12.3 liters at a pressure of 40, increased to 60. So in this particular problem, we're looking for a pressure, right? So what I need is when I'm done with my calculation, no, we're not looking for pressure. We're looking for a volume. When I'm done with this, I need to make sure that I've got a volume. And so the volume that I'm looking for looks like it's going to be liters. So I need some kind of liters here. So since I'm looking for liters, I'll go ahead and write the 12.3 liters in the numerator, right where I want it. And the pressure is at 40 and it goes to 60. So if you had a gas and you increase the pressure on it, what would the size of the gas be when you finished? Be smaller. Okay, so I simply need to take the 40 and the 60 and set them into this so I get a smaller number than 12.3. So that'll give me 40 millimeters of mercury and 60 millimeters of mercury. The millimeters of mercury cancel out. So we've got 8.2. That sounds good. Didn't bother with the equation. All we did was look at the situation and determine how it should come out and then set up the equation effectively. So the next one, I've got 25 gram, or a gas at 25 degrees Celsius occupies 3.6 liters at a pressure of 1. What will be the volume at a pressure of 2.5 atmospheres? All right, so in this problem, is there extraneous information?
25.
Yeah, all right, it's 25, but it didn't talk about it again, so that means it must have stayed 25. Okay. In this problem, we're looking for a volume, just like we were before, so it looks like we have liters, so I'll go ahead and put liters here. And what I've got is 1 atmosphere and 2.5 atmospheres. So this is basically the same problem as we had last time. So 3.6 liters, and then I've got 1 atmosphere and 2.5 atmospheres. The atmospheres cancel. Why did I put the 1 on top? I need the liters to go down because I apply at a greater pressure, so then the thing should get smaller. And what do we get here?
1.44.
Sounds good. Okay. Do that. All right, so for this next problem, we've got 600 milliliters, air at some temp. What is the volume of this new temp? All right, so we need to figure out what a volume is. So another volume problem, looks like milliliters we can use this time. We're given 20 degrees Celsius and 60 degrees Celsius. What's the first thing that we need to do when we see one of these gas law problems with temp? All right, so gonna go 273, so 293, and then 273, so 313 K for both those. So the air's at 20, and then it goes to 60. So if you had air and its temperature rose, what would happen to the size of the air? It gets bigger, expands. Okay, so what I need is 600 milliliters here.
It's not 333?
Oh yeah, sorry. So I have 600 milliliters here, and my temp is going up. So what I need is for the volume to go up. So that'll give me 333K and 293K, and then that'll be milliliters. 6.82? How about 682? Okay. So now I've got a gas at 900 milliliters at this temp and a new temp. Same problem, right? I've got an increase in temperature and I want to check what happens to the volume. So 273. So I got 300K and 273. 405K. So the temp goes up, so the volume must be going up. So I've got 900 milliliters. And then I've got 405K and 300K. The K's cancel. And what do I have for the new volume here?
1215.
1215? That sounds good. Determine the pressure change when a constant volume of gas at 1 atmosphere is heated 20 to 30. All right, so 273 gives us 293, and 273 gives us 303. Okay, and so the temps goes up, so the pressure is going to do what? Go up. So then I'm going to put the bigger number up top. And what do we get with this one?
1.3.
So something important to notice with this is, doesn't the temp go up by like 50%? Goes from 20 to 30. Isn't that like a 50% increase? Right? If I take 50% of 20 and add that amount to it, you get 30, right? How come the pressure didn't go up by the same amount? How come the pressure, since they're a direct relationship, how come the pressure didn't go up by 50%? How come that pressure isn't 1.5 atmospheres? Right, when you convert it to Kelvin, it's not that big a deal. So it's a 50% increase if I'm talking about 20 degrees Celsius to 30 degrees Celsius, but that's not what we did the math with, right? It's 293 to 303. That's a 10-degree difference, but it's a much smaller percentage of the actual overall temperature. It's a third of it, right? About a third of it, of what we would have gotten before. So, not a third of it, 3%. No, it's a lot less. And so, of course, we're going to have a lot less pressure change. So don't look at a temperature that doubles and then expect the pressure to double because of that, unless we're talking about it being in Kelvin. If it would have been 100 Kelvin going to 200 Kelvin, then the pressure is going to double, for sure. But when we're talking in Celsius, that doesn't count until we convert over to Kelvin. All right, so now we want to talk about single replacement reaction here. All right, so what, if it's a single replacement reaction, which one of the two substances is going to get taken out of the binary compound? Which is what?
Manganese.
The manganese. So the manganese gets booted out. Why doesn't the oxygen?
Because it's oxygen.
That's not a reason.
Because in that form it's aqueous, the manganese oxide is aqueous.
It's not aqueous. To have a binary compound, I have to have something that's negative and something that's positive. I can't have cadmium and manganese in the same compound because their options are they either have zero charge or they have positive charges. So I can't have them both, I can't have a compound made of those things. So I have to have something that can be an anion and something that can be a cation. And since the metals can only be cations, I can't take the non-metal out. So I have to swap my cadmium in for my manganese. So when I hop that over there, so which version of cadmium did you guys pick? 7? Is that right? Oh, it's cadmium. Do we even have any options? No, cadmium's only possible charge is either 0 or 2 plus 2. So then this is a CDO and an Mn. So that's a solid and that's a solid. And that guy's a solid, and that guy's a solid. How come the two compounds are solids? Do you have a solubility rule for cadmium or a solubility rule for manganese? You don't, neither one. Do you have a solubility rule for oxides? Yeah, and what's that rule? They're not soluble. Okay. And balancing, what do we want to do with that? I think it's 7, 7, 2. 7 cadmiums, 7 oxygens, 2 manganese. All right, that looks good. So if I start off with 243 grams of copper and 275 grams of silver chloride, how many moles of each product will be made? Okay, so this is a similar to what we've been doing before. We're just stopping one extra, one sooner, right? We're not going to grams, but we still need to basically do everything that we normally do. So does that really say copper and silver? Oh. That doesn't go with that. I just realized that. That's a totally different question. Huh. Okay. So if I've got, all right, so copper plus silver chloride and then it's CuCl2 plus Ag, solid, that's definitely a solid, and that guy's a solid. And this guy's probably aqueous, but we don't really know that, so solid's fine. And then balancing this out, I'm going to need a 2 here and a 2 there. Are we good with that? Everybody have that all balanced out? What?
Do it that way. Because you're asking for how many moles of each product will be made.
What to do the conversion between the
You still need the balanced chemical equation.
Okay, I didn't do that part.
What did you do when you had the mole to mole ratio then? Okay, let's so I got 243 grams of copper. So let's start there. 243 grams of Cu, 1 mole Cu, 63.546 grams of Cu, and then for every 1 mole of Cu, I get, I don't know, say 1 mole of CuCl2. And then I've got 275 grams of silver chloride. And then for every 1 mole of silver chloride, how many grams of silver chloride is that? Somebody have AgCl? Really? 170? Alright, that sounds much better. 143 what? 321. Alright. Grams of AgCl. And then 1 mole. No. 2 mole AgCl and 1 mole CuCl2. Okay, a couple things with this. Why is there a 2 here? Those are coefficients for that, right? And then 1 here, same thing. 1 and 1. So those coefficients are there. So definitely needed to write out the balanced chemical equation. And can you see why the first mole to mole ratio is 1 to 1? How many coppers does it take to make a copper 2 chloride? 1, right? Every time I put 1 copper in, I can get 1 copper 2 chloride out. So that's why the ratio is 1 to 1. Why is the ratio 2 to 1 here? Because I'm going to make some substance that has 2 chlorines in it, and the chlorines don't come from any other part of the problem. So I would need 2 AgCls to make a molecule that's got 2 Cls in it. That's why 2 Cls, 1 Cl2. That's why that works out like that. And it's kind of easier to see in this one because it's just 4 things. All right, so do we have a number of moles for the copper chloride here? For the first one? How about the second one? Point 9? All right, so my limiting reagent is what? The silver chloride is my limiting reagent, right? So I'm going to run out of silver chloride the moment I make 0.959 moles of copper 2 chloride. And how many moles of each product will we make? Okay, so then I'm going to do another one to figure out how many moles of my silver is going to be made here. So I'll go 275 grams of AgCl, 1 mole AgCl to 143.321 grams of AgCl. And then for every 2 mole AgCl, I get 2 mole Ag. So why is it 2 moles and 2 moles? That's what the chemical equation, balanced chemical equation says, right? Can you see why it would need to be 2 and 2? Yeah, if I've got 2 AgCls, I'm going to need 2 Ags. It's going to produce 2 Ags, 2 silvers. All right, do we have a number with this one? Okay. So my answer is that 0.9 and that 1.92. Is this super helpful for normal people? I need a mass, right? So that having the number of moles isn't super helpful for me. But that's what this one wanted. Write the combined gas law equation and then solve it for T2. All right, so the equation is T1 P, no it's not. It's P1. Okay, so there's the equation, and I just want to solve for T2. So T2, P2, B2, T1, P1, B1. We all good with that algebra? Find the final volume. 300 milliliters. Okay, so we're looking for a volume, and I've got a 300 milliliters. So 300 milliliters is what I'm going to start with. And I see some temperatures, so I'm probably just going to want to go ahead and convert those straight away. So 273 and 12, 285. And then 273 and 50, 323, okay? All right, so let's look at the temp part first. What does the temp do? It goes up. So how could you, if the temperature went up, what would that do to the volume? It would make it go up. Okay, so then I'm gonna put my two temperature units in here and then put the number 323 in the numerator and the number 285 in the denominator. How come? I need the volume to go up because of temperature, and so I have to put the bigger number in the numerator so I can get them to get that 300 milliliters to climb. So then my kelvins cancel out. And now I have a pressure change that goes from 750 to 360. So this is millimeters of mercury. And what do we,
The 750 is on top.
a pressure change from 750 to 360. So what happened to the gas?
And the pressure is down.
The pressure went down, right? So if the pressure went down, what would that do to the size of some gas pocket if I'm not squeezing it as tightly? It's gonna get bigger, right? Are you okay? Everybody okay with that? So then the bigger number goes on top. Okay. So I got 750 and I've got 360. And the millimeters of mercury cancel out and all I have left are milliliters. So what do we have with this? And we have a number? All right, that sounds good. $708. Did we use the combined gas law? The actual equation? Don't need to. We just need to recognize what's going to happen in these problems. So I've got a pressure, gas is reduced from 1,000 to 750. As the volume of the container is increased from 75 to 320. What's the final temp? The original temp is 110. So let's add 273 to this. So we get 383 Kelvin. All right, so I need a temp, so I'm going to go 383 K. All right, so we were given pressure first, so the pressure drops. How do I need to change temperature to get the pressure to drop? If it gets colder, the pressure is going to drop. Okay, so then I'm going to put the 750 millimeters of mercury in the numerator and the 1,000 millimeters of mercury in the denominator. So this will make my number go down. Let's check our pressure. So the volume of the container, I'm checking our volume. So the volume goes from 75 to 320. So what happens to it? The volume goes up. So what would you need to do to a gas to make its volume go up? I need to raise the temperature, right, to make it hotter, to get the gas particles moving faster. So I need a bigger temperature because of my piston movement. And so I'm going to run my 320 on top, and I'm going to make my 75 on the bottom. The milliliters cancel, and then I'm left with Kelvin. So somebody have a number there?
Do you want us to convert it back to Celsius
So give me a Kelvin number for a second. So in a standardized exam that you guys will most likely be seeing, this is going to be answer A. What's answer D? Why is this going to be answer D and this going to be worth full credit? We started with degrees Celsius, so by default you should answer in degrees Celsius. So this caused a probe, like a $200 million probe that we sent to Mars like 15 years ago to crash and burn. Somebody from Europe sent somebody from America some information, and the speed was, I think it was meters per second, and then we sent the number back in miles per hour. They were expecting to get the meters per second number back, and they got the miles per hour number back. So the way that that probe was working is they were just going to allow it to come down and just hit the surface. But they had built these airbags, and the airbags were just supposed to take the blow, and then the probe was going to go leave. And the airbags were too small because they didn't have the correct speed at which the object was going to impact the surface of Mars. So if somebody gives you a unit in if somebody gives you a number and there's a unit attached to it, and you need to give them back something, you should give it back in the same unit. Especially if it's a temperature thing, right? I mean, is anybody going to be like, okay, so it's 1226? Nobody wants to hear that. I mean, obviously, you're not going to have a 1226 number for a person, but nobody's going to want to hear 298 either. That's not something anybody's going to want to deal with. So yeah, convert it back into Celsius. Uh-huh.
Why is the pressure, why is the 1,000 milliliters of mercury on the bottom?
What is this problem saying?
If the pressure is reduced,
Uh-huh.
the volume increases.
What is the temperature?
Okay. If you had a balloon and you squished it, you applied pressure to it, what would it do?
Yes, ma'am.
Get smaller. If you had that balloon and you walked into a freezer, what would it do? Get smaller. No, separate instance.
Oh,
So I got a balloon, I'm just holding it here, and I walk into the freezer and I watch it. What's it going to do?
sure.
What happens if I walk into the freezer, got this balloon, and I squeeze it at the same time? It's going to get smaller, right? It's definitely going to get smaller. But why is it going to get smaller? I added pressure to it, so gases get smaller when you add pressure, and the particles are slowing down because the temp is dropping. Does one have anything to do with the other? Does my decreasing the size of the container have anything to do with the fact that I stepped into a freezer? So they're totally independent of each other. So don't look at this problem and see there's a volume change and a pressure change. How's that going to change temperature? Look at this problem and say there's a volume change. Or sorry, there's a pressure change. How does that change temperature? Okay, and then separately, there's a volume change. How does that change the temperature? Okay, this one's a little harder than the other ones because they're doing opposite things, right? So what was more important in this particular problem? The pressure change or the volume change? The temp went way up, right? So whichever one was making it go up was more important, and so in this case it was the volume one, right? Yeah, the volume one. So the volume one in this case was more important than the fact that I also reduced the pressure.
That makes sense.
So don't look at the parameters relative to each other, look at them relative to what you're trying to calculate. What is the temp of a steel container at 50, 0? What's the final pressure in the tank? Okay, this one's pretty straightforward. 273, so 143. Okay, and what is this? 2100. So 273. So 2373. Okay. And so from that to that, and it's 50 kilopascals. Okay, so I'm looking for a pressure. So I'm going to write 50 kilopascals here. And then what's gonna happen to this pressure? Is it gonna go up or go down?
It's gonna go up.
I heated this stuff a lot, right? So heating a gas would cause the pressure to go up. So I'm gonna go ahead and put my 2373K in the numerator and my 143K in the denominator. Cancel the K's out. Somebody have a kilopascals for me?
830.
Say again?
830.
830 kilopascals. That looks good. Any questions about that?